So I didn't actually know what to put into this presentation because it is some of the EDA stuff is quite technical. So I tried to divide it up into a way where I thought reasonable, in a way where you can kind of get an idea of how we created the EDA. So that's the first part of the session that I'm going to dedicate this bit to. And then after that, I'll just kind of highlight the intended use and what we saw and what we tried to remedy, and actually what the point of the EDA actually is. And then there's this kind of secondary purpose that it could be used for, uncertainty quantification, which I will talk about in the second half of the session. So just to introduce, introduce everything, I think you guys have seen this slide once before already, but the purpose is, I mean, you have the ERA 5 global reanalysis on the left, which uses a vast data set that you can refer to the website to. And a very similar data set is used on the regional reanalysis that we're doing here. So if you think about it, that the number of observations that we're using per unit area goes up quite dramatically. So that's something to bear in mind. So we've got a lot of observations, which means we need to thin them appropriately, but it's good to have a lot of data so we know what we're talking about. Okay, so the main purpose of the EDA as it was created for CERRA was for the B matrix, and that's all the design considerations went into that. And for those of you who are not too clued up on what that is, this is just a covariance matrix that describes the errors in your initial conditions, and we need these initial conditions to initialize the NWP models. But there is this possibility of a secondary potential use, and it can give us a rough guide to the uncertainty and reliability. So I will go into that in the next part of the session. So at a glance, I thought it would be good just to compare the ERA 5 data set, which, as many people have said before me, is a very successful thing, and it was quite a successful project. But ERA 5 is actually acting as an input to the limited area model that we're using for CERRA in Harmony. So that's why I've put CERRA Harmony up there, because Harmony, which stands for Halem Aladdin Research Mesoscale Operation NWP in Europe. All these acronyms are a mouthful, but there you go. So it's not good to kind of look at it in a way that we're comparing ERA 5 with CERRA, but it's good to know the differences between the two. So the major differences that we have is the resolution, as has been mentioned a few times before, the time period that they both run for. And also there is a new element in the way we create the B matrix for the regional reanalysis or the CERRA in comparison to the ERA 5. And I will go into that in detail. I mean, you'll notice that here, I don't know if you can see my pointer, but for ERA 5, there was an offline 62-kilometer 10-member EDA that was done for the climatological part, and an online part which updates every single assimilation cycle. And the one we're doing here for CERRA is slightly different, and I will go into detail about that shortly. I also put the perturbations thing down here because I wanted to make it clear that, for example, if you were worried about uncertainties in the model, that's not something that can be had out of CERRA's EDA, but that is something that was done in ERA 5, and you can get that from ERA 5. So there's a clear distinction there. So you'll notice in ERA 5, I've said the observations and the SST and the stochastic perturbation of physical tendencies was included in ERA 5, whereas in CERRA, it was just observations and SST. So this is roughly how we create the B matrix using the CERRA-EDA. You've got two main parts, one on the left, so that's two EDAs. One EDA was meant to represent the summer period, So we used a 2017 summer period, and the other one was meant to represent the winter period. And when I say here the online mixing, and then I put time of offline differences, these EDAs were run offline at high resolution at 5.5 kilometers, because 5.5 kilometer EDA is very expensive. And we mix as we move through time. So for example, if I was in January, I would use, or not I would use, but the EDA would therefore present a B matrix that is weighted 100% on the summer differences and none on the winter, to give you the correct seasonal weighting in your climatological B matrix. And if you were in March, for example, this part of the B matrix would then comprise summer, 50% summer and 50% winter. And this changes throughout the year linearly. So that's just to keep the, that was for the seasonal variations, which I'll show you, variability, apologies, which I will show you why that happens later on. And then, so that on the left is the offline part. The online part is on the right, and that's run at slightly lower resolution, actually half the resolution, 11 kilometers. And we're just taking a 2.5 day moving average out of that and incorporating it with a 20% weighting on all of those differences to give you the whole B matrix. And we interpolate these 11 kilometers to 5.5. So then you calculate the B statistics, you get your B, and down here, down here, you then insert the B matrix into the deterministic run every 2 days. So that's the way we do it for CERRA. So what's new about this is the part that I've highlighted in the middle, in this part here. The climatological high-res runs, there is an online time-dependent mixing going on between the two seasons that I just showed you before, the summer and the winter. So that's the kind of the new part here that's not been offered before. And the purpose of each of these parts is the red one, which is the climatological one, is to address seasonal variability, okay? And the blue one, the online EDA, is to address daily variability. And actually we found, which I'll show shortly, that it can account for large-scale variability, but that wasn't its intended purpose, but that's actually something that's come out of it that's quite good. So I'll show you some results on that now, or shortly. So what I'll do first quickly is to show you an idea of the variability. I got a bit jealous that everyone was showing really nice pictures and the EDA is kind of a dry, boring thing. So I tried to include some pictures. So what I want to show you here is the potential variability that you can get from two sources, the daily and the seasonal. So what you're looking at here is you've got specific, in the order from left to right, down to bottom, you've got specific humidity, temperature, volticity, and divergence. And these profiles are the sigma B profiles. So these are the standard deviations. And you've got in blue, the winter, and in red, the summer. So you can already see that they're wildly different. So that's something you need to account for in your B matrix. So that's the seasonal variability shown right there at a glance. And then the lots of little lines that you can see is the statistics for every single day in that respective month. So for example, the summer one I used, I think I put the period down there. I used days 1 to 20 in July, and each of those lines is every assimilation hour within every single day, because we do four assimilation cycles per day. So right there, you can see how much it varies on a daily basis and how much it varies on a seasonal basis. So that's something we intended to account for, and it does do that quite well. So another thing here that I kind of deem as good news was what I was talking about before, is the weather regime, or the large scale, because the weather regimes is a large scale feature that it can account for. So what I've got here is the total sigma B for temperature at 500 hectopascals. This graph is quite a mouthful, but I thought it would be good to show. Blue is March 2003. The red one is March 2018. And we tried lots of different proportional weightings between the online EDA that I showed you before and the offline EDA. And you can see that the solid lines, for example, are 100-0, which means it was weighted 100% on the climatological matrix and 0 on the online EDA. Then you've got 80-20 with the crosses. Then you've got 50-50 with the dots, 20-80 with the squares, and then the little triangles are 100% weighting on the online EDA and nothing from the climatological part. And then the green dashed line that you could see at the top is what it would look like if you had a totally static B matrix with just the climatological part. And the black vertical lines are the parts where I show there is a major weather regime change in those periods that I tried. And you can see, for example, the most telling one is between days 21 and 27, where there's quite a drop in the sigma B, because it actually changed from a blocking regime into an NAO plus. So that's a North Atlantic oscillation. So it changed accordingly, and it only took a few days to do the change, which is actually very good. However, there's a caveat, which leads me to my next plot. So that variability seems to only happen when you have plenty of observations, which is why I'm showing this plot. So in March 2018, we had on average around 80 to 90,000 observations in the particular period, in comparison to March 2003, which was the other case that I showed on the other plot, which had an average of around 30 to 40,000 observations. So from this, you can kind of conclude that the B statistics can detect a change of weather regime on a regional domain, which is kind of good, but it depends on the observation. So I wouldn't expect this, for any dates behind 2003. So that's that. Now, moving on to the uncertainty quantification part.
2 minutes left.
Okay, cool. So I thought it'd be quick. And just outline the kind of sources of error. You've got initial condition error and you've got model error. And we're not accounting for model error in any way in CERRA. One of the things that model error is important for is highlighted by this image that I took from one of Tim Palmer's material, which I think is really good. Even if your model was absolutely 100% perfect, because of the chaotic nature of NWP models, you don't know which side of the wing you'll end up on, especially if you are right in the middle of the attractor and you're just about to leave the end of the attractor. So that's something that we need to keep in mind. So now I'm going to just show you an example that you could use the EDA mean, because we have available for CERRA-EDA, we can make available the EDA mean and the EDA standard deviation. So you can get an idea of the spread in the mean. So this, what you're looking at here, an image that I took from Lisette Edvinson, thank you very much. And this is showing the EDA mean. So if you then couple that by looking at the EDA spread, you can see here, like over Norway, there's quite a lot of spread. And down there near the south, like southeast of Italy, there's a bit of high standard deviation there. So the way you can kind of interpret that is these are the parts where I wouldn't trust the data as much, but that's as far as it kind of goes with that. So the advantages of the EDA, if you want to use it for uncertainty quantification, is it can show uncertainty in the data, and it can give you some idea of the observation coverage, because those standard deviations could be for observation coverage or not. And then there's a list of disadvantages because it doesn't account for model error and so forth. And that's it. I hope I didn't run over time. Thank you very much.